Let me just share the screen. So basically what I want to show, this will be like modeling kit for EnergyRt and with export to switch, with link to switch, and also PIPESA. So this is work in progress. I drafted the generic idea like a couple of years ago, but a lot of changes have been since then. And what I want to show today, like just simple first step, how to get the map or use PIPESA map and the data from mirrored data, not from ERA. So you will have options. So basically what will be done, let me show you. Okay, this is actually, I opened this map for Bangladesh to see if there is a good potential for wind. It's maybe not great, but still there is some potential. So what I'm going to show, it will be published, pushed here. At least scenarios we're not going to publish. I will just generic scenarios, generic scripts will be pushed here on this revaluation, renewables energy evaluation, because the idea of this modeling kit was like to re-evaluate renewables, and the model will be designed specially for that. Okay, I think that's it. And what I'm going to discuss today is how to get the map and how to get the mirror to data for the map for your country. Right now, this is just a little bit of R scripts. You already have some. For several countries, you already have from PIPESA several maps different. So I just want to show you how to do it in R, how to read them in R. So or have another one. So basically, here is will be script like get the map, something like that, or the map. You will just this example how to do it for different countries. And I have Colombia here. I don't know why. Just one of the downloaded from PIPESA. I got two countries only. So right now we're doing for Colombia, and this is a database which also I think your PIPESA team is also using. So you can download it using R packages easily. So and there are so many like growing number of formats for JS information. One of them is GIS, but in R also you have like at least 3 to 5 different like formats. For example, this one is vector format. It's kind of a newer one. Then you can transform it to spatial polygons or simple features. And this is a script just to show it how to do it. This is simple features for Colombia. And you also can do, why different formats? Because several packages have different packages, libraries have different features. And sometimes one work better than another, or one have more features than another one. Again, this is what we're going to use. This is ggplot. Mostly we're going to use with simple features, but also sometimes you can use in different format, which is like special polygon more. It's kind of older. So also this is from PIPESA dataset. And if we look at the files for Colombia, here is how many different JSON, GeoJSON you have. So I just picked several of them. You can read it directly and plot them. So for example, this one is the same, but from PIPESA files. so there are, this one is Voronoi, and so what I'm just going to show that it's connected. So this is one, like, I don't know if it's 10 regions or what it is, and this one is for offshore. Okay, that's it with the maps. You can, I mean, this is the easy part. You can, I mean, a couple of years ago, it wasn't easy for me, at least, because it was like a lot of try and something working, something not. But now it's kind of done, and it's easy. This will be shared. Another one is capacity factors for wind and solar energy, at least. So again, you can use, like, for example, this 10 region onshore map, and like use these shapes to get to build your model using PIPESA ERA data, or alternatively there is a MIRA data. ERA is European Space Agency, MIRA is NASA, so they have similar data sets. So some people like ERA data more. I have comparison. We did it for our India project. It's actually pretty similar. So for India, at least, what we did. Anyway, there are options to use. There will be another data source, which is NREL, National Renewable Energy Laboratory. They have API, but this data has to be downloaded per each location. But it's more precise, maybe for wind at least, because it has, for some countries, it's available, for some not. This is the issue. But also for some countries, it's available with 15 minutes resolution, which might be like, in some cases, it might be desirable, especially when you model for India and there was half an hour switch, I mean, shift between data and the actual time in India. So this is why we might want, like, if we have real data for consumption and we want to match it with wind and solar, this will be like some inconsistency. Anyway, okay, so let's see what's, so this is MIRA tool dataset. It's massive, and we like 3 years ago we tried it for China, and actually we downloaded a lot of data, and it takes time to understand this data set and get the right time series from it, because it's massive. So it has a lot of libraries, and just you can spend a lot of time learning it. So basically, we found what we need exactly for renewables, and we downloaded them for 41 year, 1980, 2020. So there will be update maybe January or February with 2 more years. But the point is, it's already downloaded and compressed, and we put it on here. If you go to repository of like EnergyRt, you can find here. You can find here MIRA tools package right here. So this one is has some documentation. It's not polished, but it's functional version. So polishing takes time, so this is not very polished. Anyway, so what it's saying, this is manuals. This is exactly what this pages, and here is the data set itself right here. So we just it's about it's less than 300 gigabyte, but it's a lot of data, and this is description. It's very compressed format, which is FST. We are going to use it here. Only few variables, but for every hour and for the global, and global for the entire world. So here is how to use it. and actually here is some description also. For example, here is locations. So we had to name every locations. It's more than 200,000 locations with, depending on where you are, it will be like 50 by 60 or 50 by 50 or a little bit different. So, but you got the point. So this is, again, this is the whole data set to estimate renewables. And so it has wind speed and at 50 meters and 10 meters only. It has temperature, what else? Solar radiation, actually, wind direction, I don't know if it's needed for someone, temperature and solar radiation, two variables right here. And also there is not straightforward way to use this data and convert it to capacity factors, because you have a lot of steps to do, like how your panel will be located, will it be tracking or not, and so on and so on and so on. And here are like two different versions. I mean, for solar power and wind power, I would say it's just rather like generic approach how to do it. If you want a more refined version, I would suggest to just to go dig inside deeper. But in general, with all the uncertainties in the data, which is not direct measurement, of course, but it's and all this stuff which is not completely like accurately measured. So with this approach, we still have a pretty good guess. And so this package also gives you some estimation of capacity factors for different types of trackers, like fixed horizontal, fixed tilted, single axis horizontal tracking, or tilted tracking, or vertical tracking, or dual system. So, and because it's not like, it's pretty comprehensive model, we had to repeat some, I mean, there are several ways how to calculate. We just, what is data set, sorry. We reproduce some of them available models from NRL websites. And it's actually several steps. And here is how every step is calculated. You can see every variable just to learn how it's calculated. So that's it. So this is the generic idea how to go from solar radiation to production with different PV systems. So this is, for example, horizontal. This is dual tracking, and they have different production and different time and different location based on your system. So we have validated data with NRL PV watts model, and it's pretty close. PV watts has exact locations because it's measured, and this one mirror is like per cell, which is pretty big, and it's actually compared for different locations. There are sometimes in both in mirror and PV watts, there are some excessive spikes in both of them, but this is just the way it is with aggregation and models. But in general, they're all the same. They're pretty close. And for wind it's actually, I would say, we will have much lower accuracy for wind, because wind is very diverse across location. If you have 50 by 50 cell, inside this cell, you will have a lot of differences, and you have average for 1 hour for this area. This is one point. Another point is height of the wind. So we have in mirror 50 meters, in area we have 100 meters. We compared it, and actually they're very close. I think it's just I mean, exactly. So what is happening here? You can see the, you can check what will be the algorithm, how to calculate. We take generic power curve aggregated from several types of like mainstream turbines, and this is how to calculate. Okay, I'm going back to just a few more minutes. So what we do here, we have to install Mira Tools package, which is available here on the website. Get started. You can see how to do every step. For example, you have map, and you can select locations for your map. This is what is happening here. So we have first what we do, we overlay our GIS, our map with Mira and with Mira Grid. In this you will have the cells. So basically what it's doing is it's cutting cells using borders of cells and regions. So if you have different regions, it's better to rerun to have different aggregations. Okay, so then what you do, you extract from the data set. You have to download the data from here, just because it's pretty big. So what you need to do, you need to download it from here, yeah, or from Zenodo. So you have two options. You can pick by month. If you want 1 year, just 12 of them, and all other files which are not. So this one is, for example, 1981 October, but you can download like for 1 year only, but also you need all other files to make sure that it's working properly. You don't need, if you're not going to use the whole 41 years, you just use for year you want. Okay, so basically, so what you're running the script, and you have selected right here for 2020 from first hour to the last hour of the year. You have this data set. So what we discussed, it will be time, location ID, wind, and solar radiation. Also, there is precipitation and a couple of other variables. We're not using them. So then you need to pick some locations which have higher potential based on the whole time series, 40 years of weather data. And if we look, I mean, it's already aggregated and stored in the package in the data set. For example, Mira2 mean 41 years, it's actually mean values for every variable for 41 years. And this one is wind speed at 50 meters. And for example, another one will be like solar radiation and precipitation if you're going to use it. So finally, we need to estimate capacity factors for solar and wind. And what we discussed here before, we can run some algorithms to calculate plan of array radiation, which is actually almost production, but you need also add some systems to convert from DC to AC. This is not done because we're not doing it, but what we need how much radiation will be on the panel based on different tracking system. So this is calculated for 6 different tracking systems. And finally, then we move to estimate capacity factors based on this radiation. So this is done. I mean, this algorithm you can check. I'm not going to stop longer because it's already a lot of time, and that's it. So what we want to have as an output, we want to have, so this one is like production, average annual production for 2020 for different system types, fixed, horizontal, or tracking, dual tracking. T means tracking, and the second will be like L mean tilted, H horizontal, V vertical, and so on. So finally, you save this information based on for your GIS. We can add later offshore as well, but right now it's not. I mean, the map is without, but you can use PIPESA map to get offshores data for offshores and so on. So the same for wind. We have the same wind capacity, and for example here for Colombia, you will have pretty low potential for wind. And if we want to filter them, like capacity factors more than 20% a year on 100 meters height, it will be only a few cells. This is what we have for Colombia as far as mirror data tell us. So that's it. That's it. And I think that's it. So this will be saved, and the next one will be based on this data. So we will use it to build the model. So these steps, I mean, it will not take much time to do it. I will share it like maybe early next week. But right now, later today, I will push it on GitHub and send you an email saying with this video and saying this is done also. I think that's it. Any questions?
But Oleg, so again, the question remains same: how we can use the data in case of switch?
Yeah. So we have already tried to use switch data in EnergyRt and EnergyRt data in switch. So it's doable. So what I'm going to write some scripts to read pipe size data in R and save it in both for both models, for R and for switch. So this is what I'm going to do. But I need a little bit learning time because I'm new to PySide for the data set. So at least the maps are already here. So maybe it will be not so difficult. We'll see.
Okay. Thanks, Oleg.
Okay.
Oleg, a quick clarification question. Have I understood properly that regions which we are using to aggregate renewable potential can be set quite flexibly? So it may be administrative regions, it may be shapefile of Voronoi partition, or it may be any other shapefile which we choose to select.
Yeah, you're right. So I mean, for renewables, we need, the map with all the regions and like offshore and onshore. This is where we use the map. I mean, maybe you also need some to calculate distances for your power lines, for transmission lines, but that's it. So where we use the map, we have to identify data points from MERA2 or from ERA. So we need to understand which locations we need to take from the data set. So then we take the data set. Then on the second step, since like for Colombia, for example, it's 300 data points, locations. 300 plus locations. Then we decide, do we want to aggregate it or we don't? So do we want to aggregate it for every by regions or cluster them somehow, and so on. So this is where we design can use map to identify which mirror points will be located overlay with every region. So one mirror point can actually go to 2 regions or 3 regions because it will be split by borders of the region. So you can calculate the area of the splitted mirror point and put it use it like a weight for your aggregation, something like that.
Okay, thanks a lot for the detailed explanations. And one more quick question. You have mentioned that there are still data inside the package which account for 41 years of climate data.
Mm-hmm. Yes.
Do you mean annual resolution or monthly?
It's a 1 hour resolution for the world. Yeah.
It should be quite a big data set.
Yeah, we use package FST, which is, we compressed all this data into 270 gigabytes and pushed it in cloud, which is this one. Okay, I'm not sharing. You can go to Zenodo and Google it. Search it like mirror tools, mirror to data, and there will be like one file per month, but it's for the globe and for the 1 hour resolution. Yeah. So
thanks a lot.
Yeah. To squeeze it, we had to like a little bit cut. Convert them into integers. To scale, convert it into integers and squeeze with a very high compressed format. Okay.
Sounds as an amazing approach.
Okay. Any other questions? Okay, thank you so much, everyone, for 3 years. Oh, 3 hours. First long meeting, yeah, 3 years. Okay, for 3 hours, yes, again, I thought this will be shorter, but I think it's a lot of information we have to digest. And thank you, everyone, to PIPESA team and for participants.
Oleg, Oleg, can you just stay back for 1 minute? I just want to talk to you something else.
Oh,
yeah.
Yes. Okay.
Oh, for others, it is nothing very, interesting to you guys. So that's why I just wanted to talk to Oleg.
Okay. Thank you so much. Thank you, everyone. See you next week. Bye.
Bye.
Thank you, Oleg.
Thank you, Oleg. Thank you, Oleg.
Thank you,
Thanks,
Oleg.
Max. Yeah. Thanks, Anas. Yeah, everyone.
Thank you all.
Thank you, everyone.